see. Okay. Okay. Sorry, let me. Um,
Okay, so I think we should start if you if you agree. Yeah. It's my pleasure to introduce Professor Christian Ketterer from Maynooth University. He's going to speak about gluing spaces with Bakry Emery Curvature bounded from below. Please, Christian.
okay. Thank you. And thanks for the introduction and for the invitation to speak in your seminar. Yeah, it's a pleasure to be here. Yeah, so in this for this talk, I will gluing spaces with Bakry Emery curvature bound from below. And let me first give you some rough overview. So I mean, so we will have 3 or 4 parts. I mean, I first tell you about the gluing construction for Riemannian manifolds. Then I will state some theorems that connect this to curvature bounds. Then I will explain about Bakry Emery curvature and the curvature dimension condition for metric measure spaces. And then in the end, I show you a theorem how this relates to gluing constructions again. Okay, so let's start with the gluing construction. So so what does it mean when we glue together Riemannian manifolds? So the setup will be that we have 2 Riemannian manifolds that are n-dimensional and have boundary. And the boundary we assume is connected and compact for simplicity. And and then what we have is an isometry that identifies these 2 boundaries. And the isometry is with respect to the induced Riemannian metric on each of these boundaries. And if we now want to glue these 2 manifolds together along the boundary, the first step is that we build the topological gluing. So this is obtained by defining the following quotient space. So we have the disjoint union of M0 and M1. And we have an equivalence relation on this disjoint union that is given as follows. So X is related to Y if and only if X is mapped to Y via the isometry. And this is when X is in the domain of I or Y is in the range of Y. And in all other cases, we just assume that that X has to be equal to Y. So in this way, I mean, we can glue together these 2 manifolds along the boundary by identifying boundary points using this isometry. This is not just a topological construction, but there also exists a smooth structure on X that respects the underlying smooth structure on M0 and M1, in the sense that there is a smooth structure that contains both of the smooth structures M0 and M1. And therefore X is not just a topological space, but it's again a smooth manifold. And then, so this concerns the smooth structure, and now we also want to glue together the Riemannian matrix. The straightforward way to do that is, so we define a C0 Riemannian metric G simply by saying G restricted to M0 is G0 and G restricted to M1 is G1. This gives us a C0 Riemannian metric because on the boundary where we identify M0, where we glue M1 and M0 together, because of the isometry, we can identify G0 and G1. So this is just a C0 Riemannian metric in general, but it already allows us to make sense of geometric properties like distances and volume. Concerning the distance, there's another way how you can define it. So the distance function related to this Riemannian metric, we also can build as follows. So we can look at points in our space X, and we first define a pseudometric or an infinity metric that is defined as the distance between X and Y with respect to G0 or G1 if both X and Y are contained in M0 or in M1. And if they lie in different parts of the glued space, we just set it infinity. With this pseudometric, we can build now an honest metric on X as follows. So we again pick 2 points, X and Y, and we look at all sequences X0 till Xn that connect these 2 points. We sum up the distances of consecutive points in this sequence, and this gives us the length of this polygon that is generated by the sequence. And then we take the infimum with respect to all sequences, and this results in a finite metric on X. And we call the result, we call the space X together with this metric the metric glued space. So, to illustrate what is going on, let me show you this picture here. You see here M0 and M1 are the 2 manifolds that we glue together along the boundary, that is this red line. And then we have the 2 points, X and Y. And we pick sequences that in some sense connect X and Y, and we look at the distances between consecutive points and sum these up. And so we get the length of this polygon, and then we minimize with respect to all with respect to all such polygons. Okay, and the advantage of the second construction is, as you notice, it only relies on the metric structure of M0 and M1. So, so in particular, this makes sense for any metric space. Okay, so now, and let me give you another picture to illustrate what is happening. So this is now a way how you can glue together Riemannian manifolds, and an example would, for instance, be like something like this. You have this squared shaped domain in R2. You take that, you fold it, and then you take a copy of that, turn it around, and then you can glue these 2 copies together. and you get a cube. So in this sense, the cube here is a glued metric space that we get from gluing together two copies of this rectangle. Okay, so this is about the gluing construction in general for metric spaces. And now we also want to bring in curvature bounds on Riemannian manifolds. So let me just briefly recall the relevant curvature notion that we want to consider. So when we have a Riemannian manifold, there's the famous Riemannian curvature tensor that is defined using the Levi-Civita connection, and it's defined on triples of vector fields like this here. Yeah? And nabla is the Levi-Civita connection. With this curvature tensor, we get the sectional curvature. This is obtained by looking at pairs of vectors that are orthogonal and normalized, and plugging this into the curvature tensor, the sectional curvature of the plane generated by these two vectors. And the sectional curvature of such a plane, one way how you can think about it tells you in which way the curvature differs from standard flat geometry. So I mean, if you have a point where if you have a plane where the sectional curvature is positive, it's more curved like in Euclidean space. So from this, we also get another curvature notion, that is the Ricci curvature, which we obtain as follows. So we pick one vector v, and then we pick an orthonormal basis that completes this vector v here to an orthonormal basis. And v should be w here probably. And then we look at all sectional curvatures that of planes that are spanned by together with the vector w, and sum this up, and this is and the result is what we call the Ricci curvature in direction of w. And you see, by definition, it's sort of a mean a mean value of sectional curvatures, and it's also a two tensor, so we can compare it directly with the Riemannian metric, and we can speak about lower curvature bounds. And and so now, going back to our gluing construction, the question is, so what can we say if our Riemannian manifolds that we glue together satisfy such curvature bounds? So let's assume they satisfy a Ricci curvature lower bound in the sense I just showed you. And the question is, does the glued space also satisfy a lower curvature bound? And in which sense does it satisfy this? Because notice the metric G here from the gluing construction is not smooth. So, I mean, a priori, we cannot define Ricci curvature. So we have to come up with a way how we can make sense of lower Ricci curvature bounds. Okay, and one way how we could do that is, so we define Ricci curvature bounded from below for the glued space as follows. We say that there exists a family of smooth Riemannian metrics on X, such that the family G delta converges in C0 sense to the metric G that is the glued the gluing metric, and this happens when delta goes to 0. And moreover, the Ricci curvature of this matrix G delta is bounded from below by K minus epsilon, where we then say epsilon goes to 0 and delta goes to 0. So this is, let's say, an ad hoc way how you can make sense of lower Ricci curvature bounds for glued spaces. And similar, we can also define lower sectional curvature bounds if we want to. Okay. So with this definition, now I can state the first theorem. So I mean, this is a classical theorem, so I didn't prove that. So and for that we need one more notation. So we have our boundaries of the Riemannian manifolds, and on the boundary we have the so-called second fundamental form, which encodes the extrinsic geometry of the boundary inside of a manifold. And it's defined for pairs of vectors that are tangent to the boundary in this way. And this is by differentiating the normal vector field along the boundary in direction of these two vectors here. So what we notice is, so I mean, we have two Riemannian manifolds with boundary that is isometric, but I mean the two fundamental forms are depend on the extrinsic geometry. So I mean, for each of these Riemannian manifolds, the fundamental form on the boundary will eventually be different. But with this, now we can make we have the following theorem, and this goes back to Perelman. So he proved, so if we assume a lower Ricci curvature bound for each of the Riemannian manifolds M0 and M1, and moreover we have that the sum of the corresponding second fundamental forms pi 0 and pi 1. If this sum, that is now a two form on the boundary, is non-negative, then we get below by K. In this generalized sense that I showed you before, that means that we find with almost with Ricci curvature almost bigger than K. So this was proved by Perelman at some point in the 90s. And later this was generalized by Kozowski. He observed that, I think his proof was actually different from the one of Perelman, but he observed that and you also get that the glued space satisfies sectional curvature in this generalized sense. And he even observed in this situation that you get an if and only if. So this assumption on the second fundamental forms is not only sufficient, but it's also necessary to get a lower sectional curvature bound on the glued space. So at this point, one could ask, is this the same is true for Ricci curvature? And when Perelman proved this here, I mean, he was not interested, in fact, in the other direction. So I mean, he didn't make any comment about this. But we will see later that, in fact, also in the case of Ricci curvature, we have an if and only if here. Yeah. Okay, so this is the classical theorems about gluing constructions. And let me, at this point, say something about why is it useful to look into this. So the first point I want to mention here is that when Perelman proved this theorem, I mean, his main motivation was not the gluing itself, but he wanted to construct new examples of manifolds with positive Ricci curvature. And what he managed to do is, using his gluing theorem, he was able to show that connected sums of CPNs in fact admit metrics of positive Ricci curvature. And he was able to show that this way that you can construct metrics with positive Ricci curvature and arbitrarily large Betti numbers. So this was interesting for him at this point because in general we cannot expect that connected sums of manifolds with positive Ricci curvature again will carry a metric with positive Ricci curvature. And this is simply because of the Bonnet-Myers theorem that tells us positive Ricci curvature implies that the first fundamental form, the fundamental group is finite. So therefore, you cannot just glue together manifolds arbitrarily and still find metrics of positive Ricci curvature. But still, in this case here of CPN, Perelman could show that this is possible. So this is one application. Another application is that when you have manifolds with boundary, by using these gluing constructions, you can extend your manifold in a quantitative way, and also preserving the Ricci curvature. And this will result into compactness theorems for the class of Riemannian manifolds with boundary, and having a Ricci bound and a bound on the second fundamental form. And this was observed by Wong and then later used by Yamaguchi and collaborators to show interesting results about collapsing Riemannian manifolds and estimates for the inscribed radius. And a final application I want to mention, this is more recent, that using these gluing constructions, Cucinotta and Mondino were able to show that manifolds with Ricci curvature bounds have a so-called half-space property. And this is a sort of Bernstein theorem for submanifolds that are contained in this product space M times R. So this is a very recent paper where they also use gluing constructions. Okay, so these are only few examples why this is useful and important. So now let me come to generalizations of this. So one thing we can observe from the theorem of Perelman is that when we have this Riemannian matrix G delta that converge in C0 sense to G, this implies also Gromov-Hausdorff convergence of the corresponding metric spaces. From this, one obtains that this generalized notion of Ricci curvature that I showed you, in fact, implies that the metric glued space itself satisfies a generalized notion of Ricci curvature. And more precisely, this metric glued space is a so-called CDKN metric measure space. So this is a space that so where CDKN means it is the curvature dimension condition for metric measure spaces in the sense of Lodge, Storm, and Villani. So I will explain in a second what this is. And similarly, when you replace Ricci with sectional curvature, what you get is that this limit space will be an Alexandrov space with curvature bounded from below by K. So I will not explain Alexandrov spaces, but I will only explain the CDKN metric spaces. So let me give you a brief excursion on or a brief yeah, brief explanation for this type of spaces. So the curvature dimension condition is a way how you can define Ricci curvature for metric measure spaces that are not necessarily smooth. And the idea here is the following. So we look at the metric measure space, and we have we also have the space of probability measures on our metric measure space, and the metric structure lifts to the space of probability measures in form of the Wasserstein distance. So this is a distance that one can define between probability measures, and it's defined in the following way. So so you look at couplings between these two probability measures, and and a coupling is a measure on the product, is a probability measure on the product space, and because it's a measure on the product space, you can integrate here the distance square, and you can see and you can try to minimize this or you can minimize this this integral here with respect to all couplings, and this results in a distance between these two measures, mu0 and mu1. And this distance now allows you to study the geometry of the underlying space. And this happens in the following way. So I mean, we take or we consider entropy functionals. And for us, the relevant entropy will be the n-Rini entropy that is defined in this way here. So mu is decomposed into its absolutely continuous and singular part. We throw away the singular part, and we integrate the density of the absolute. And we can see this as a function on the space of probability measures. And what this entropy measures is how spread out your measure is. So you can see this when you look at the extreme case here. So if your measure mu is just singular, then the entropy in fact vanishes. So which means because of this minus sign here, the entropy becomes maximal. So therefore we have this entropy, and we can now and the idea of curvature is or the idea to define curvature using this notion is as follows. So we say a metric measure space satisfies the curvature dimension condition C0n if for all measures mu0 and mu1 there exists a length minimizer with respect to the Wasserstein distance, and this is a curve that connects these two measures, mu0, mu1, in the Wasserstein in the space of probability measures, and such that the entropy is convex along this curve. Okay, so this is a very so this was a quick introduction to the curvature dimension condition, and we will see this again in a second. But I mean, let me give you an important class of examples now that that satisfy this curvature dimension condition. And this this is the class of smooth metric measure spaces with so-called Bakry Emery and Ricci curvature. So a subclass of all metric measure spaces are Riemannian manifolds, of course. A distance and a measure, so it becomes a metric measure space. we also can choose a different reference measure than the Riemannian volume. So we can replace the Riemannian volume by a measure that is given via some density function times the Riemannian volume. And the density function here is the function phi, as you see here. And we always assume this function is smooth. This is why we call this a smooth metric measure space. And it's also convenient to write this density phi as in the following form. So we write it as e to the power v for another smooth function capital V. Okay. And so where does this show up? So this was studied already before the curvature dimension condition, because these weighted spaces appear in the diffusion operators of the following form. That is the diffusion operator LF, that is the sum of the Laplace operator with respect to the Riemannian metric, together with a drift term that comes from this density function V. One can observe that this operator is directly related or appears as the generator of the Dirichlet form that we get when we replace the Riemannian volume in the standard Dirichlet energy with our new reference measure. So this was studied already before in the 80s, especially by Bakry and Emery. And they observed, okay, if we are interested in properties of this operator, it's convenient to introduce a new tensor. And this is the so-called Bakry Emery tensor that is defined in this way. So I mean, it's a combination of the Ricci tensor together with a new term that comes from the density function, and it also involves a parameter n that plays the role of a dimension of this metric measure space. And you see here the definition is as follows. So when n, capital N, is equal to the dimension, we just get the standard Ricci curvature. If n is infinity, which is a parameter that we allow, then the n Ricci tensor is simply Ricci plus or minus the Hessian of V, and all n Ricci tensors in between are defined like this here. Okay. So this was introduced by Bakry and Emery, and then later studied also in terms of its geometric properties. But let me first give you some examples. So I mean, one example where this shows up is when you have an interval together with a density, like e to the power b that equals phi, and then because an interval has no intrinsic curvature, the n Ricci tensor just becomes this expression here of the second derivative of v minus this term that involves the first derivative of v. And in this form, you see then that a lower bound for the n Ricci tensor is the same as a Riccati inequality for v. Of this form, which again is the same as this type of differential inequality for the function phi, where here so it should be phi to the power 1 over n minus 1, where here also should be some power to 1 over n minus 1. And what you also see when k is 0, I mean, this is exactly convex. I mean, the inequality here is just convexity for this function phi to the power 1 over n minus 1. Okay. Another example, I mean, where this explicitly shows up is when we have the following example. So we can look at the interval 0 pi, and the weight may be sine to the power n minus 1. And if you do the computation, you see that this metric measure space satisfies n Ricci curvature bigger or equal than n minus 1. So in some sense, this has the same curvature behavior like a sphere, like an n-dimensional sphere. Another example is when you take Rn together with the density that comes as this Gaussian density. And if you compute the infinity Ricci curvature for this, you can observe that it is bigger or equal than 1. So in this sense, the Gaussian space has infinity Ricci curvature bigger or equal than 1. Okay, so these are examples, and let me give you some more properties of spaces with Bakry Emery Ricci curvature lower bounds. So we look at some weighted space, and when we have and we also allow that there is boundary now. And if we have Ricci curvature and Ricci curvature bound from below by k for such a weighted space, what we get is that this weight here will be always strictly positive in which is a good property. So which means this measure cannot have singularities at some point. And another thing is that it's that we have a monotonicity with respect to the parameter n. So the Ricci curvature, the n Ricci curvature, if the n Ricci curvature is bound from below by k, then also the n prime Ricci curvature is bound from below by k if n prime is bigger or equal than n. Bohne-Meyer's theorem, like for the classical Ricci curvature. So if the n Ricci curvature is bounded from below by n minus 1, the diameter of the space is bounded from above by pi. So this you can see, for instance, in this example of the interval 0 pi that exactly fits into this situation. And finally, we also have a Bishop-Gromov volume comparison result, or Bishop-Gromov volume monotonicity result. So you see the properties of this Bakry Emery n Ricci tensor closely resembles the classical properties of Ricci curvature lower bounds. Okay, and one final theorem that connects this now again to the curvature dimension condition. So if we have a weighted space with Bakry Emery n Ricci curvature bound from below by k, then the resulting metric measure space is also a CDKN space, and also the other way back. So I mean, if we have a smooth metric measure space that satisfies CDKN, then it also satisfies Bakry Emery and Ricci curvature bound from below by k. So where this result is proved by contribution of all of these people that you see here. Okay, so this is all. So this is in some sense our introduction to the main theorem that I want to show you now. So we are interested now in the gluing of such weighted Riemannian manifolds, and if we are able, and also if into the question if curvature bounds are preserved, or Bakry Emery Ricci curvature bounds are preserved under gluing constructions. So for that, let me fix the setup here again, or let me first give you an example. Sorry. So an example here would be that we have two intervals with a weight that we want to glue together at one point. And we assume that these weights here satisfy this differential inequality, which means that that the Bakry Emery n-Ricci tensor is non-negative. And then we can build and then we can glue these two intervals together at their common point C, and we can also build a weight on this new interval AB. And the question here is now, so when is the resulting weighted space again, or when does the resulting space again satisfy a Bakry Emery lower Ricci curvature bound? Or does it satisfy a curvature dimension condition? And the observation is that we can make here, it satisfies the CDKN condition if and only if phi is concave, or here I write if, but I mean if phi is concave. And when is phi? When can we say that phi is concave? So the necessary and sufficient condition for phi being concave again is that the two one-sided derivatives of phi 0 and phi 1 at C have to satisfy this this inequality here, because I mean concavity means that that the derivatives are monotone decreasing, and so this is a necessary and a sufficient condition for phi being concave again. So this gives us a hint what should be a condition for that, or what should be a condition that we need when we want to glue together weighted spaces. So let me fix again the general setup. So I mean, we have two weighted Riemannian manifolds with boundary, where both satisfy Bakry Emery n-Ricci curvature bound from below. And we also have that on the boundary, the weights coincide. And then we can define a new weight on the glued space that we call phi here. And the question is, when does the weighted glued space, that is the glued space together with this weight here, satisfy again a curvature dimension condition or a Bakry Emery Ricci curvature bound? And the answer I can give you in this theorem here. The theorem says now, so I mean, we have two weighted spaces, and the n-Ricci curvatures are bounded from below by k. Then we assume that again the sum of the second fundamental forms on the boundaries is non-negative, and we have this condition here, which maybe looked rather complicated, but you see this is this here is the derivative of the weight in normal direction at the boundary, minus the trace of the second fundamental form pi 0. And we on the where we look at one into normal direction. So this expression here, if you look at it closely, is something that that was already studied. So this is what we call the mean curvature of the boundary of the weighted space. So you see, if this first term would not be there, I mean, minus the trace of the second fundamental form would be just the mean curvature, the standard mean curvature. But with the weight here, we have a new mean curvature that is given by this expression. And the second condition, therefore, says nothing else than that the sum of the mean curvatures should be non-positive. And the result is now that if these two conditions hold, or these two conditions hold if and only if the metric glued space together with this weight phi is a CDKN space. Yeah, so this is the main result. We can say even more. So we can say that this metric glued space also can be obtained as a limit of n-dimensional smooth Riemannian manifolds that satisfy a lower Ricci curvature bound in the classical sense, where this n here, this capital N, is or this n in the bracket. So this is the smallest integer that is bigger than the parameter n here. Okay. So this is the main result. And what I want to emphasize is that this generalizes the result of Perelman regarding gluing and classical Ricci curvature, but it also improves this result in the sense that we have here not just that we do not just have one direction, but we have an if and only if statement. Or true if with this weight is a CDKN space. Okay, so let me also give you a case of the theorem. So one special case is when you just have one Riemannian manifold with boundary and Bakry Emery and Ricci curvature bound from below, then you can glue two copies of the same manifold together, and this is the doubling space. And these two conditions reduce to non-negativity of the selectivity mean curvature on the boundary. And two conditions hold, or these conditions hold if and only if the doubling space is a CD 0n space, where I restrict myself here to zero curvature bounds. And here it is interesting to note that the second condition can be translated into a more into a geometric statement. So this mean curvature bound in combination with Ricci curvature is nothing else than that when we apply this drift Laplacian to the boundary, to the distance function to the boundary, then this is non-positive. Or in other words, this distance function to the boundary is superharmonic if with respect to this drift Laplacian. Okay. So this is the main theorem, and before I will say a little bit about the proof in a second. But let me also say there is also a new paper by Philipp Reiser and Francesca Tripaldi who also proved one direction in the theorem, and they so they don't prove the only if part, but what they do is they prove such a theorem and they use it to give similar like for Ricci curvature to give new examples of spaces with positive Bakry Emery Ricci curvature. So they really go into the study of the geometric consequences of such a theorem. Okay, and so let me say a little bit about the proof. So I mean, so for the proof, I had the following idea that appears also in other contexts. So the idea is that when you have such a weighted space, you can build a warped product, CR, and the warping function here, as the warping function, we choose our weight. And then you can encode the information of the weighted space into a warped product that is now not weighted anymore, but it's a standard Riemannian, it's a usual Riemannian manifold with the Riemannian volume. This construction works in particular nice with Ricci curvature. So here's the metric that you would get, and with Ricci curvature, the behavior is as follows. So if you compute the Ricci curvature of this metric, you get this lengthy formula here. What you can observe in this formula is that that you get here this term in psi directions or in xi directions, and you get this other part here in the v direction. So the v direction is the one that where of the second factor in this warp product. And you can notice that this formula, the first part here, looks very similar like to the Bakry Emery N-Ricci tensor, and indeed it is the Bakry Emery N-Ricci tensor with respect to this weight here. And so the idea is now, if you choose if you plug in this parameter r in front of the second factor in this warp product, you can make this second factor in the Ricci tensor as small as you want. And you can say if the Bakry Emery N-Ricci tensor was bounded from below by k, then the Ricci tensor of this warp product is bounded from below by k. So you can translate information about the Bakry Emery tensor into the Ricci curvature of this warp product. And moreover, you can observe, if you now look into at the boundary of this warp product. So the boundary of the warp product is just the boundary of the space Mi times the second factor in the warp product. If you do some calculations, you see that the second fundamental forms have the following nice estimate again. So the conditions that you saw before in my main theorem translate into conditions for the second fundamental form of the warp product, which is precisely the condition you need to glue them together again. So this is therefore what we do. So we glue, and moreover, we also get an isometry between the two boundaries in the warp product. And so what we can do is we can apply the theorem of Perelman and Kozowski, and we glue these two warp products together and see that they satisfy Ricci curvature bound from below by k in a generalized sense, where we have here this parameter r still flowing around. But now you can send this parameter r to 0, and in the limit you get the weighted space back again, which then, because these generalized Ricci bounds are stable with respect to this type of convergence. Because of the stability, we get that this weighted space in the limit again satisfies Ricci curvature bound from below by k, and more precisely, it satisfies the CDKN condition. So a priori, this is the CDKN condition with this bracket n, but I mean you can improve this to the full CDKN condition with the n that we saw before. So this is roughly the idea for one direction in the theorem. So we exploit the properties of warp products and we can reduce the proof back to the result of Perelman and Kozowski. And for the reverse direction, this is more technical. For the reverse direction, what I did here is I apply a technique that is called the 1D localization. That is a very useful method that you can use to prove results for CDKN spaces, and it was very useful for proving the reverse direction in the theorem. Okay, yeah, this is all what I wanted to say. Thank you very much, and I hope there are some questions.
Thank you so much, Christian, for the great talk. Is there any questions for Professor Ketterer? I guess I should ask a question myself. So,
Yeah, please.
if there is any questions, you're welcome to ask. And so, can we say something about continuations of Ricci larger than K? Like, because you have gluing, so if you reflect with respect to the boundary, and like, so is there any conditions that we can extend a manifold with boundary? We can extend it a little bit further from the boundary so that it still has Ricci larger than K symmetry.
Yeah, in fact, yes. So this is yeah, that's a good question. So this was what I mentioned in this application. Oh, where is it? Yeah, here. I mean, I'm not sure if you can see it. So I mean, there's this paper of Wong who exactly did what you were asking. So when you have a Riemannian manifold with Ricci curvature bound from below, and there's boundary, and you have two-sided bounds for the second fundamental form of the boundary. Then Wong showed that you can extend the boundary, or you extend the manifold beyond the boundary a little bit by essentially what you do, you glue a collar to the boundary. Yeah? And because of this theorem of Perelman, you are able to control, or I mean, what you say, I mean, I mean, what you do is first you define a collar that will give you an extension, and it has and this collar under conditions has a Ricci bound, and then you can glue this collar to your original manifold, and because of Perelman theorem, the this extension will also satisfy a lower Ricci curvature bound, and not just any Ricci bound, but in a quantitative way, so that you really have on the Ricci curvature uniformly, and then you have this extension, and you can then or yeah, you can prove compactness results for this manifolds with for this extended manifolds, and therefore also for the manifolds. And so in fact it's a good question if some construction like this is also possible with Bakry Emery Ricci curvature.
Oh yeah, thank you.
I think, I mean, maybe, I'm not sure, I guess maybe you,
No, that
you
was
work,
great. Yeah, that's
yeah.
I
I
was
mean,
thinking that locally you can reflect with respect to the boundary, and you get the same. You should get the
yeah,
same. So
yeah,
actually,
I mean, now I remember what you said. Yeah, exactly. So it's kind of a reflection at the exactly. Yeah, you have the boundary, and you first find this neighborhood of the boundary, and then what you do is you can reflect this neighborhood to the outside of the manifold. Yeah, exactly. This is how it's done. Yeah. I
okay.
think, I mean, maybe you and Christina worked. I mean, didn't you? I think I remember that. I think I'm familiar with this result because of your work with Christina, but I don't know.
That was a long time ago. So perhaps maybe. Yeah, that was it was great. I mean, I really liked. So yeah, that's. So what about you have
Yeah,
lots there are
yeah,
doing theorem, but like this can this be like sort of give you new
yeah. I
things,
mean,
maybe like some new things in Alexandrov setting?
yeah. That's also a good point. Probably what would be interesting would be to I mean to prove such a result also in an Alexandrov setting when you have a weight